Students, in the previous session, we talked about the concept of electrical capacitance, wherein we studied that every conductor or every conducting body has a capacity to hold the charge. And the electrical capacitance of the conductor is a measure of its ability to hold the electric charge. So suppose we consider any conductor, let's say this is a conductor which is carrying a charge of Q, because of which the potential is V acquired by this conducting body. So in that case, the capacitance can be expressed as C is equal to Q upon V, and accordingly the SI unit can be written as coulombs per volt, or it is expressed in terms of farads, as 1 farad is equal to 1 coulomb per volt. Now based on this concept, today in this session we are going to find out the capacitance of an isolated spherical conductor. So what do we see here? Suppose this is a isolated spherical conductor of radius r, which is carrying a charge q uniformly distributed over its surface. Now, since q is a charge on the surface and r is a radius of the sphere, then what will be the potential at any point on the surface? Potential V at any point can be expressed as 1 by 4 pi epsilon naught Q by R, considering this charge to be concentrated at the center of the sphere. Then from the expression for the capacitance, from the concept of capacitance, as C can be expressed as Q upon V, if we substitute this equation for V over here, we can express capacitance as 4 pi epsilon naught R. So we can say that capacitance of any spherical conductor is equal to 4 pi epsilon naught R, or in other words we can say that the capacitance of a spherical conductor is proportional to its radius. So more the radius is, or more the size of the spherical conductor, the more will be the capacity to hold the electric charge. Now based on this concept, let us find out the capacitance of Earth. We know Earth is a conductor, right? So assuming the Earth to be the spherical conductor of radius 6400 kilometers, let us calculate its capacitance. So using the same formula for the capacitance of the spherical conductor, we can write down C is equal to 4 pi epsilon naught R, where radius can be taken as 6400 into 10 raised to the power 3 meters. Now the numeric value of 1 by 4 pi epsilon naught is 9 into 10 raised to the power 9. So from here 4 pi epsilon naught can be written as 1 by 9 into 10 raised to the power 9 into 6400 into 10 raised to the power 3. And when you solve this, finally you will get 0.711 into 10 raised to the power minus 3 farads. Right? So you can see, just consider this value, just look at this value of the capacitance. It is such a small value, not even equivalent to 1 farad. So you know the size of the Earth is huge. You know the radius of the Earth is around 6400 kilometers. So how big the size of the Earth is, and such a big sphere is not having even the capacitance of 1 farad. So from this we can get an idea that 1 farad is actually a very large capacitance, right? So in terms of microfarad, we can express capacitance to be 711 microfarads. So generally in normal practice, in practical requirements, generally we have the capacitors of capacitances in microfarads or picofarads, right? So from here we also get an idea that an isolated conductor cannot have a large capacitance, right? As we see, even a isolated Earth, which is a huge conductor, even that conductor is having such a small capacitance. So practically when we are going to design a device which we name as capacitor, the purpose of this capacitor will be to hold the charge, to hold the electrical energy. Then our aim will be just to design such a device which will have the maximum efficiency. So here maximum efficiency will mean it may have the maximum capacity to hold the charge. So as the isolated conductor cannot have the large capacitance, so now let us see that how we can increase the capacitance of any conductor. Increase the capacitance means how can we increase the capacity of that conductor to hold the charge. So for this, let us consider, suppose this is a metallic plate, right? I name it as E, and it is positively charged all around. Positive charge is distributed uniformly throughout the sheet, right? Now, because of this positive charge, it acquires a potential, let's say VA. Let's say VA is the potential of this positive plate. Now, what I am doing, just see, I just place an identical plate close to it. Identical conductor, we can say. I just place an identical conductor close to this charge plate. Then, as we know, what will happen now? Due to the induction, the negative charge will get induced on the closer side of the plate A, right? And on the farther side, let's say this plate is B, on the farther side of plate B, positive charge is induced. Okay? Now, how it is going to affect the potential of this plate A? The potential of the plate A decreases due to the presence of this negative charge on the closer side of plate B. The reason behind this, because let VA will be the potential due to this positive charge on plate A, but because of the negative charge, the net potential will be decreasing, because इस plate के negative potential के कारण भी यहाँ पर at the location of A there will be potential, right? So we can say the net potential VA will be minus of we call it, say, let's say V1, where 1 is the closer side of plate B and 2 is the farther side of plate B. Okay, but because of the positive side of this plate, anyhow there will be increase in the potential, let's say V plus V2. Okay, so what do we see here? That because of the presence of this plate B, which was not charged, which was a metallic plate, the potential of plate A is getting affected. Because of charge 1, charge on the closer side, the potential is decreasing, but because of the charge on the farther side, the potential is increasing. Okay, but since phase 1 is closer to plate A, then the effect of the potential, that is decreasing in potential, will be more dominating factor. The dominating factor will be because of the negative charge, because it is closer. Now see what we are doing. So net effect will be in that case anyhow, because of this first phase the potential is decreasing, because of the second phase the potential is increasing, but anyhow the impact of first phase is more. That is why the net potential of plate A is going to decrease. Now further what we can do is, let us see once again. Now suppose I ground this plate B. Suppose I ground this plate. You know the meaning of grounding? Let's say we take a wire and just connect with the plate B and just ground it. The other end is grounded in the earth. Then what will happen? This negative charge is bound to plate A, right? Will be bound to the positive charge of plate A. So the positive charge on the other side get neutralized. The electrons from the earth, they just neutralize the positive side. So that finally what we have obtained now? We have obtained this plate A, which was having the positive charge all around. Okay. And now when we remove the grounding, this negative charge is distributed on plate B. Because the positive charge is neutralized, and now we have this plate B, which is purely having the negative charge. So which is like distributed uniformly throughout the plate. Now what will be the net impact on the potential at point potential A, potential of plate A? Obviously now because of the negative plate, because of the presence of plate B, the net potential will be the difference of the two potentials. Now we see that the presence of a neutral conductor is actually decreasing the potential of a positively charged plate, right? Now Capacitance is equal to Q upon V. We know that capacitance is equal to Q upon V. For the same charge, if we decrease V, what is the impact on C? Definitely the C is going to increase. So we see that by just placing an uncharged plate, an uncharged conductor close to a charged conductor, we have decreased the potential of that charged conductor, which in turn increases the capacitance of that conductor. So this is how we can increase the capacitance of any conductor. Or in other words, we can say that the capacitance of an isolated conductor is considerably increased when we place an earth connected conductor near to it. And such a system of two conductors is named as capacitor. Such a system of two conductors. So how do we define a capacitor? Capacitor can be defined as an arrangement of two conductors separated by an insulating medium that is used to store electric charge and electric energy. So this is how we represent symbolically a capacitor. A simple parallel plate capacitor. We name it as a parallel plate capacitor. So what does it consist of? It consists of the two identical plates which are placed close to each other and are separated by a small separation. And that separation, this gap, can be either air or it can be filled by some insulating medium. And the insulating layer between the capacitor plates is commonly termed as dielectric. So basically it is an insulator. Basically an insulating material is introduced between the two plates which are placed parallel to each other, close to each other, but here we name this insulating material as a dielectric. Why do we call it dielectric? We are going to discuss. And the same is the working principle of the capacitor as well, which we discussed just now. So if you are asked the principle of capacitor, so how do we state the principle? Capacitor works on the principle that the capacitance of a conductor increases appreciably when an earth conductor is brought close to it or brought near to it. So these are the images of some capacitors which are used in the electrical circuits. So these are the different types of capacitors of different ratings. Different rating in the sense of different capacitances, generally in microfarads or picofarads. So this is basically a cylindrical capacitor. So there are various shapes of capacitors, either the two parallel plates separated by an insulation, or you can say a cylindrical capacitor. So what is basically a cylindrical capacitor? The two conducting cylinders are separated, are placed coaxially like this, and this separation, this gap between the two cylinder is filled with some dielectric or some insulating medium. So these are also the paper capacitors or the various capacitors which are used in electrical circuits. Now let us talk about dielectric. What is a dielectric we are talking about? It is basically an insulator with a quality of polarization. Because of this quality of polarization only we name it as dielectric. Or we know that a non-conducting material in which the induced charges are produced on their faces on the application of an electric field are called dielectric. So why do we call this non-conducting material or the insulating material as dielectric? Because the way they behave in the presence of the electric field, that is why they are termed as dielectric. And definitely the conductor is not an insulator, so it cannot be a dielectric. So dielectric can be only the insulating material, right? So depending upon that how these insulators are behaving in the applied field, we classify the dielectrics as polar and non-polar dielectrics. So first of all, we'll talk about polar dielectrics. What are polar dielectrics? These are the molecules of dielectrics in which the center of mass of positive charges do not coincide with the center of mass of the negative charges are called polar dielectrics. And the examples are water, HCl, NH3, carbon monoxide, etc. So as you can see in this example, this is an example of a water molecule or HCl molecule. So here the center of this hydrogen, which is a positive charge, and the center of the chloride ion, they do not coincide, they do not overlap over each other, right? So that there is a certain separation or a certain distance between the positive and the negative ion, between the center of the positive and the negative ion, so that they behave as an electric dipole. You know, they are the equal and the opposite charges which are separated by a small separation. Same way in case of water molecule also, we can see two hydrogen ions. The positive ions are the hydrogen ions and the negative is the oxygen, this one, right? So the center of positive hydrogen and the center of the oxygen ion are not coinciding over each other, so that they also behave like a dipole. So this can be taken as plus ion and the minus. They are not coinciding. There is a small separation, let's say two-way, where this is the center of the H ion and this is the center of the oxide ion. Okay, two H ions and H2O, right? So this also behaves as a polar dielectric. Now, what happened? Suppose these are the two plates of the parallel plate capacitor, right? If I connect them through a battery like this or a cell, then what will happen? One of the plate which is close to this positive charge, which is close to the positive terminal of the battery, will acquire the positive charge, let's say plus Q, and obviously the other end will acquire the negative charge. And there is a potential difference developed. If this is V, then anyhow gradually the total charge is Q and the potential difference developed will be V between the two plates once it is fully charged. Because there is a separation, there is a gap or an insulation between the two plates, so it won't conduct. The current won't be flowing between this positive and the negative plate, but anyhow the electric field is developed, as you can see through these lines. This will be the direction of the uniform electric field. Although across the edges we can say there will be bending of the electric field line, but anyhow for the small gap we can ignore this bending effect, which is also termed as a fringing. Okay, so we consider majorly in this region in between the two parallel plates the electric field will be uniform. Now in this uniform electric field, suppose yes, this is a positive charge plus Q and this plate is negatively charged having the minus Q. Okay, now these, when it is filled with some dielectric, let's say water molecules, a dielectric made of water between the capacitor plate is inserted, then initially these small dipoles, each molecule of hydrogen is equivalent to an electric dipole whose dipole moments will be randomly arranged, right? There won't be any specific pattern, so that even if each molecule is associated with an electric dipole as well as a dipole moment, but since their orientations are random, right? ये minus q है, ये plus q है, suppose this is plus q, this is minus q, this is minus q, this is plus q. So all the dipoles are randomly arranged. That is why the next dipole moment will be equal to 0. There is no dipole moment. Okay, but when this electric field is applied, this will be the direction of the electric field. Then what happens? What do you think will happen? Initially, they were randomly arranged. Okay, on the application of this external field, which is in this direction, right? These dipoles start arranging themselves, start align themselves along the direction of the electric field, in the sense of these green circles are representing oxygen, which is negative, and these pink colors are representing the positive ions. Okay, so if this plate is positive and this plate is negative, okay, so for all the molecules the negative will start orienting towards the positive, and the positive will start orienting towards the negative plate, like this. So this is how you can see these molecules which were randomly aligned, so that the net dipole moment was 0, but now they start aligning themselves according to the applied electric field, so that gradually what will happen, this end of the dielectric will become positive, overall positive, and this end will become negative within the dielectric. Okay, so that inside the dielectric a field is developed, let's say that is E dash. An internal field is developed within the dielectric. So what is the net electric field now in this region between the two plates? Applied field was E. An opposing field is developed because of the orientation, because of the alignment, of these small dipoles. So the net electric field will be the difference of the two fields, or we can say that the electric field is reduced. Electric field is reduced. Now, if the electric field is reduced, from the expression we know E is equal to dV by dr. This is the relation between the electric field and the potential difference, right? So if here let's say dr will be the separation between the two plates and dV is the potential difference. So anyhow decreasing the value of E, for the same value of dr, dV will also decrease, or the potential difference will decrease. The potential difference will also decrease between the two plates. And again, from C is equal to Q upon V. For the same charge, decreasing V will ultimately increase the value of capacitance. So that is how we see that what is the role of dielectric. What is the role of dielectric inside between the parallel plate capacitors, between the capacitor. So first of all, we are using a system of two parallel plates so that the capacitance can be maximum. Secondly, we are filling this space between the two plates with a dielectric so that the capacitance can be further increased. Now this is how we are seeing that how a polar dielectric is increasing the capacitance of a capacitor. Now let us see what are non-polar dielectrics and how they are increasing, how they are able to increase the capacitance. First of all, let's see what are non-polar dielectrics. The molecule of dielectrics in which the center of mass of positive charge coincides with the center of mass of negative charges are called polar dielectrics, and they are the hydrogen, oxygen, carbon dioxide, etc. So here, ideally, it is something like this. The center of the positive is coinciding with the center of the negative, so that there is no net dipole moment, because the center, there is no separation between the positive and the negative charge, right? They are just coinciding with each other. So such dielectrics are called non-polar dielectrics, right? Now what happened when these non-polar dielectrics are placed between the two charge plates of a capacitor? Now again, let's say these are the two plates. One is this plate, right? The other is this one, plate of the capacitor, which is having the minus charge. This is plus Q, and let's say this is having the minus Q. So that again there is an electric field in this region E. Right. Now, when we introduce these molecules of non-polar dielectric, then what happens? This end is positive and this end is negative. So because of this applied field, the centers of the positive and the net negative charges, they displace. Somewhat like this. Suppose this side we apply the positive field and this side we apply the negative charge. Okay. So, according to this figure, I need to consider this is negative and let's say this is positive charge. External field is applied in this direction. Then what will happen? The positive charge, the positive ion will get attracted towards the negative side and the negative will get attracted towards the positive side. So that now the dipole moment is created, which was initially not there. Okay, so somewhat which you can see over here also, like these centers which are coinciding, now the negatives start depositing on the left side of the dielectric, within the dielectric, and the positive charge will finally be towards the negative plate within the dielectric. So again we can see that inside the dielectric an electric field is developed. That is, let's say E dash. Now again, what is the net electric field? We can say the net electric field will be E minus E dash. So this is how in case of non-polar dielectric, how the electric field is reducing when applied in the external field. So again, with the same reason we can say, since the electric field has decreased, so consequently the potential difference between the plates will also decrease, and we know when V decreases from C is equal to Q upon V, capacitance increases. So V decreases and capacitance is increasing. So this is how we design a capacitor. So what is basically a capacitor again? It is a system of two parallel plates or the arrangement of two conductors which are separated by an insulating medium. Separated by an insulating medium. And it is used to store the electric charge and electric energy. So now in the next session we are going to discuss how we can determine mathematically the capacitance of a parallel plate capacitor. Thank you so much.